Hi, welcome to the water webinar. The open space that you see behind me here used to be the reservoir that held water that was delivered to my house. But about 5 years ago, my local water utility abandoned the reservoir because the system they used to pump water up into the hills had become reliable enough that they didn't have to worry about power outages or failures of the pumps. And so now the water that comes to my house is stored in tanks up in the hills and is released as needed. That's it. And now the water's stored in this tank behind me, and it gets down to my house by gravity the way it used to, but with a much smaller tank. In comparison, the situation's pretty different when you think about the electricity and heating system in my house. So 70 years ago, when my house was built, we had electricity coming in from the street. But now I've got solar panels on the house, and so on sunny days, my house produces enough electricity for itself. And over here, you can see where the gas comes into my house. So now I have a natural gas system that we use for heating and for hot water. But the next time that the house is remodeled, or when people build more houses in my town, they won't be able to put natural gas in because of concerns about climate change. And that brings us to the topic of today's water webinar. Why is it that the water system that brings water to my house has barely changed in 70 years, while the electricity system's changed, and pretty soon the way we heat the house is going to change? I've been thinking about this myself for quite a bit of time, and in 2017, when our today's speaker, Korneel Rabaey, came for a mini sabbatical at UC Berkeley, we spent a lot of time talking about this. Korneel had been in the process of remodeling his house, and he had been required to put in a rainwater capture tank as part of his home. And so he had been thinking about whether houses could actually live without being attached to a water grid that brings water from long distances, but actually manages to treat the houses. And that's really the topic of today's seminar. So I know he doesn't need much of an introduction, but for those of you who don't know him, Korneel Rabaey is a professor at Ghent University and one of the founders of Capture. And he's one of the organizers of this symposium series. And today he's going to tell us about ways in which we can break our connections to the water grid, the system that brings water to our homes and takes it away, and see if houses can make do on their own. Korneel, we're looking forward to hearing your seminar.
I am Korneel Rabaey from Ghent University and Capture. I'm really delighted today to talk to you about some of the views that I and others have on extreme decentralization in the water sector. So the key message that I want to get across today to you is that building smaller, very decentralized water treatment and supply systems can contribute to the water cycle because it will drive innovation, it will enable more resilience, and it will give more functionality to water systems. What I'm going to talk about is also based on a publication that we made last year, and you see the co-authors of this publication also here. So let's get started. If you think about water sector, and if you're a technologist, in many cases you think of large centralized installations like this one. This is a very big one, the Blue Plains wastewater treatment plant in Washington. Now, centralized systems like this were developed a bit over 100 years ago, certainly the treatment aspect. And they've been fantastic because they safeguarded human and environmental health. Let's not forget that's the first purpose of water supply and sanitation. They've led to more and more efficient water treatment and wastewater treatment, and they also now enable more recovery options, for example, of biogas. But they lead to major investments in transport. Water is moved away from where it is gained. Such projects typically have very long lead times, and they lead to slow innovation. I'll go a little bit more in depth on these different points. So if you take Europe, where I'm located at the moment, and you take a tiny country like Belgium, we already have many challenges in terms of water. So just a small north part of Belgium, around 12,000 square kilometers, has sewers to transport this water around. Here you see Cloaca Maxima, by the way. This is in Rome, the oldest known sewer. They tend to look a little bit more modern in Belgium nowadays, obviously, but the invested capital in sewers just for the small Flemish region where I am is over 50 billion euros. That's a lot of concrete underground. And similarly for water supply, in order to get more robustness in our system, we are increasingly connecting within our area, within Europe, water systems, large piped networks. Now, in many places in the world, it's already known that just connecting and transporting water can have adverse effects. You see an image here of Mono Lake in the United States, a well-known case where massive withdrawal of water has led to very adverse environmental impacts. So water transportation, to enable more robustness in a general grid, is not necessarily a good thing. Potable water is often transported well over tens of kilometers. You use then on site that potable and that rainwater, and typically after use discharge. The wastewater is again transported over kilometers to a centralized wastewater treatment plant typically. And then it is as a point source, almost like a factory, discharged in the river. And so the transport transports the water away from where it is gained as rainwater to where it's in the end discharged. And this has an impact, an energetic impact, and an embedded impact of these pipe networks. And this is why we're starting to think about parameters such as a water kilometer to quantify for the incoming water over how many kilometers you have transported it, and for the water that comes from a building, a house, a factory, over how many kilometers you transport it away again to be treated and discharged. Now, on another note, the centralized approach also leads to very large investments within a single project. And as a result, although the water sector finds itself quite innovative, I would dare say that we are actually a slowly evolving sector. And here you see a nice graph that was made by Danny Parker, in which he mapped out different technologies over time, their maturation from lab development all the way to a mature technology, and how many installations you have. And you see it can easily take 30, 40 years before a new technology in the water sector is really mainstream. And that, of course, has to do with the very important decisions on large-scale investments associated with, for example, putting on a whole new wastewater treatment plant. Now, in many places in the world, this is not yet a consideration even, because networks, pipe networks for water, sewer networks may not exist. But also in these cases, the transport of water produced somewhere in a centralized facility to the user can have a large impact. For example, in Kenya, it's calculated that water delivered by a truck can require almost 10 kilowatt hours of energy per cubic meter, which is far larger than the normal energy investment to produce tap water. So obviously, a solution to this is to develop more decentralized technology that locally produce water, treat water, and that thereby avoid the transportation costs. And this has, particularly for developing countries, been a very popular approach. And so I am not reinventing an approach here. many books, many literature already exist, many implementations for local water production, local water treatment. And you have programs such as the Gates Foundation Reinvent the Toilet Challenge, where we go one step further, where really localized, full integrated treatment systems are under development. Now, what I like about that Gates Foundation approach is that it forces you to think. You think in terms of challenges on where you want to be, rather starting from existing technologies. And this is very similar to me as to how an artist works. We are very fortunate with our team to work with artists. And here you see, for example, a robot that is powered by the waste that is in water to float around, to move around and clean up more water. Similarly, beautiful design by Teresa van Dongen, another artist we work with, where a lamp is powered by degradation of organic matter. And so artists come from a perspective of where they want to be and design for that. While a risk that has come through our development of centralized systems is that we think according to what they call the sunk cost effect. We are so attuned to large-scale technologies that actually, if we think about decentralized treatment technologies, we tend to just make smaller technology of what already exists. But it doesn't need to be just smaller technology, and similarly, decentralized technology doesn't necessarily need to be the cheap or cheapest technology, because decentralized technology can have also other purposes relative to centralized technology. I'll give a few examples. On the left-hand side, you see what you classically think about if you think about ultrafiltration, reverse osmosis treatment of water to produce drinking water, large-scale installation in racks. Well, on the right-hand side, you see an under-the-sink RO system as present and very popular in India. Tens of thousands of these systems are sold in India annually. And as a result, the cost of this system has dropped below $250. Not working on drinking water, but on grey water. There's this example, the Hydraloop system. This is a Dutch company that develops a quite straightforward reactor that takes the grey water in a house, so you need a separate pipe network for that, treats the grey water so you can reuse it to flush toilets or to bring it into a garden. Now, it's nice, this is a small technology, and if I get it right from the information I get on the company, it took about 7 years to get to the market, which is very different than the 30 to 40 years we discussed before. And because a company like this can roll out now many hundreds or thousands of these units, innovation may actually come very fast. And the third point on the purpose. You see the evolution of new systems like here on the left-hand side, Robinetto, on the right-hand side, Brita. Robinetto makes a system that in buildings, predominantly, you can have a water tap. You can change the properties of the water, the flavors, the experience of the water can change. So we can work with septic tank-like approaches, which was the main sanitation approach so far. We can work on grey water, and we can work on drinking water with small-scale technology, which admittedly today is more expensive. But you can wonder what the willingness is to pay for the customer. Now, an important thing in willingness to pay is also where these water systems at a decentralized level will bring you. And I want to talk a little bit about unpublished work of our group, of Arjen van der Wallen, where we've actually done a lot of simulations on home-based, single household-based water treatment systems. And we looked how we would be able to fully make a house water independent. And so what you realize if you go through the simulations if you have some storage, you can quite quickly produce a lot of water in the house because you have an input of rainwater and actually quite good technology to reuse already. Now, one thing is that if you start doing these calculations, you see new challenges coming up. If you're going to reuse water at home level, contaminants may accumulate. For example, here you see over time in the bottom, the chloride concentrations in water if we start reusing it. And we reach a limit of about, well, a standard of about 350 ppm quite easily, making the water less suitable for use. But if you do more interventions and start purging excess water, you have to get rid of water anyway from a building, then you can see that you can maintain very low salt concentrations and deal with contaminant accumulations over time. So even with a quite small buffer tank here, we managed to, at least in silico, close a water cycle at single household level. And then you can start creating performance indicators. We can say, how independent do we make this house? An independence factor. How circular is the house in terms of water? How much do we recharge to our local environment of that rainwater that initially fell on the house? And how tolerant are we to extended drought periods? And this allows you to compare systems and to start really making an assessment how robust, how resilient is our water system getting through such interventions. We're not there yet. We have a long way to go, I believe, before homes would, in an economic way, be water independent. But to get there, we can learn a lot from other transitions. I've already discussed that we have to learn also to think differently. A smaller technology is not necessarily the same as a larger technology. But we can also learn, for example, from photovoltaics, where the approach to work with very small panels and then roll out millions of panels through a very well-planned strategy led to very fast decreases of the cost of photovoltaic power. And similarly, you can anticipate a same trajectory if we have the vision for small-scale water systems. Important if you want to get the societal drive for such smaller local water systems is also that you have to engage with the customers. And the first customers who buy systems, they invest in sustainability or another aspect, and they want to be recognized for that. A system has to be visible in order to be successful in a first phase. But water systems also need to come closer. Water is a very intimate product. And this allows to actually communicate via your water system with the user of the water system and engage that user in also developing your system. This is what is called customer-driven innovation. And smartphones are a very nice example of that, because you buy a smartphone, actually you are able to also, because you interact with this device, think of new good solutions, applications of this system. And you and others are able to make new applications via apps on this platform that actually create that extra functionality. So we can think in the same way about water systems. Can we have consumers closer interacting with their small water system and thereby contribute also their creativity to it? Very important also, if we are going to work decentralized, we should not be trucking around large amount of chemicals towards the different treatment or production sites. We will have to go electric. Going electric minimizes chemical addition to the water, minimizes residues, but is also becoming very cost competitive. Think of this house that I showed before. This is an image from Tesla, the typical view on electrification, a car, an electric car, and you power up that car with the photovoltaic panels on the roof. But charging that car requires, on average, about 2,250 kilowatt hours per year. So it's very hard because you will need 15 square meters of photovoltaic panels to supply that power, and that's going to be very challenging. it will be very difficult to get this a typical home independent. But if I would use that electricity to produce the water for the household, we estimate you need about 500 kilowatt hours per year to make a house water independent. That means you only need 3 to 4 square meters of photovoltaic panels. Now that is a very acceptable amount. As I mentioned, decentralized systems can add new purposes. And we call this now personalized water systems. What we will see is that we first see a fast evolution of water systems if all goes well, because we have small systems that go through fast generations. We add in the creativity of the user via this consumer-driven innovation. This would lead in time to a cheaper water system and hopefully also a more sustainable water system. But the combination of these allows also to think about more tailored functionalities, thinking about health and thinking about the water experience. I'm going to go a little bit deeper into this water experience, because if you produce water at building, home, or small district level, you basically get what I would call empty water. It's there for now tailoring to the user's need. And so aspects such as adding pre and probiotics to the water, tailoring the water, for example, the mineral content of the water to the user taste or health requirements become feasible. And you can also address new expectations on the climate footprint of your water system, and you can really turn it into a consumer product, not the kind of nonsense of electrified water at the past, but truly water that has health-promoting benefits. Logically, you'll have questions with this. Is this safe? Well, I think also there's going to be a presentation after mine on water and data. We will have to monitor smaller systems, but it is possible now via the Internet of Things to monitor small-scale installations, and bear in mind, if an installation fails, the scale is very small. You may wonder whether this approach is ethical, because yes, more affluent people will get better water, whatever that means, at least in the first phase. But photovoltaics shows that principally such an evolution can be ethical if in time these photovoltaic panels, those water systems, become available for all at an affordable price. It's a bit similar to behind-the-counter services for which people are already making choices. But we will also need to introduce it not as a replacement, but as an extra. We are not going to get rid of large-scale systems just because there are smaller-scale systems. It becomes an extra. We need to keep on requiring that the standard system during the transition delivers the adequate water quality at an adequate price for all. I hope I have at least given you some ideas on how decentralized treatment systems can contribute, and how I feel that we should be thinking about innovation in this space. Go outside the typical innovation that we see in the water sector and look at other societal transitions. I want to thank the partners for the webinar series. Ghent University, initiated via the Strategic Institutional Partnership, University of California, Berkeley, and University of Queensland, and also Capture, the organization where I'm a CTO. I also want to thank the new journal Environmental Science and Ecotechnology for supporting the broadcasting of these webinar series in China. So I'd say send them your best work. Thank you for your attention, and I look forward to the questions that will come. It's a pleasure to introduce our second speaker for this session. And our second speaker is Professor Erik Mannens from Ghent University and imec. Now, he's going to talk about water and data. As you may be aware, we see more and more distributed systems also in water treatment and water supply. And we are increasingly measuring also online with various sensors, water parameters to, for example, safeguard safety in membrane systems. And that is generating a lot of data. And so the era of big data is truly entering also the water space. Interestingly, in Belgium, we have a project on the Internet of Water, in which several parties have come together to really start up the first distributed monitoring networks and really deal with the data sets that are originating from this. And so I'm very interested to hear from Erik Mannens, who is involved in this project, what the overall approach is there and what his thoughts are about water and data. Just before I give the floor to him, briefly, he is a professor at the Data Science Lab, and he's also the CTO of Data Science at imec. He has a PhD degree, originally also from Ghent University in 2011, and a master's degree in computer science from KU Leuven. With that, I look forward to Erik's talk and to your thoughts about it afterwards.
Hello everybody, I'm Erik Mannens, Professor Data Science at Ghent University and Research Valorization Director at the Flemish Research Institute imec, where I'm responsible of bringing fundamental and applied research from our university towards both industry, government and society at large. And today I'll be talking about 3 projects we've been doing dealing with water problems. As you will see, it mostly concerns reading and interpreting lots of sensor data with AI algorithms, hence I coined it with the term smart water. Now all 3 projects, the Internet of Water, flood prediction and smart water grid, fit into several of United Nations Sustainable Development Goals: clean water, responsible consumption, sustainable cities and climate action, to just name a few. Now, the first project is a project of the City of Things Living Lab of imec. On the photograph, you see a bird's eye view of the city of Antwerp, which harbors one of the biggest ports in Europe. In a dedicated area of the city, a few square miles wide, we rolled out a living lab, which is called City of Things, to test all kinds of IoT related projects. Within this living lab, we are using digital technologies and researching the way in which the Internet of Things technology can provide solutions to cities and regions for any urban issues. One of the projects that fits this shoe is the Internet of Water. At the moment, there are major water problems in Flanders due to climate change, as it is the 4th year in a row that we have a drought crisis in summer. Over summer, the drought committee is constantly discussing whether the orange code will apply so that governors can take measures themselves and invoke a water capturing ban for all citizens. Now, in order to better deal with such problems, a fine-meshed measurement network is needed so that evidence-based and well-founded decisions can be made. In this Internet of Water project, we mainly worked on salinization and discharges into surface water. Our permanent water sensor network is spread across Flanders in a targeted manner. The sensors measure important indicators of water quality in surface water, groundwater, and wastewater. These sensors can only map the impact of discharges of household wastewater and industrial wastewater, but also determine the impact of overflows and incidental discharges or calamities. In addition, a great deal of attention during the project is paid to our salinization problem. This will also be mapped in real time on the basis of the sensor network. The data generated will be used to develop innovative algorithms and hydrological models to model the various problems in our water system as a whole. At the same time, future evolutions will be more predictable. This creates practically useful policy information for a more sustainable water policy. As such, we contribute to a future water policy of the Flemish government. Now, how are we going to do this? Through a full stack approach, a complete horizontal approach from hardware to applications, from raw data to insights. We start with a sensor built on the basis of imec technology. This measures a number of parameters of water quality. We roll out this sensor and connect it to the cloud via the network. We also provide algorithms that guarantee the correctness of the data and minimize maintenance thereof. The data is then stored in the cloud for analysis. We also provide a monitoring dashboard and an operational process to keep the sensors active. This data is then linked to visualizations and further analytics. These analyses give us insight into the past about what happened, but if we link this data to applications and models, we can make predictions too. The permanent data stream from the sensors is an optimal feed for algorithms and these hydrological models. The managers of our water sources can respond then to this water intake, or the supply and reuse of treated wastewater and rainwater, or the reuse of effluent for irrigation, the pumping up of water in canals, and the design of new buffer basins. Furthermore, we can provide targeted advice in the context of contingency plans and crisis situations. Let's go quickly through a number of working groups that fuel this project. So, what kind of sensors do we use to develop and test the different kinds of housing? We use conductivity sensors, temperature sensors, acidity sensors, and ultrasound sensors. Here, one can see the initial measuring points on different parts of the River IJzer. River IJzer, this is where the First World War took place. Here one can see sample readings of both the conductivity and the temperature sensors at different measurements venues. Now, how do we deal with IT infrastructure and models? Now, the work group IT indicated what components and functionalities were required for such an IoT platform to work end-to-end. We need an IoT agent, which is based on the NGSI proxy agent. We need a context broker. We need a time series database for the sensor data, a metadata management platform, for example, to put the location model in. We need different APIs. We need verification of algorithms for drift countering, and we need some basic authentication and modeling building blocks. The approach is aligned with the principles chosen at the start. So the content management, the metadata and device info is needed at the beginning of the chain, and in the end we link it towards European approaches as a basis for the data first strategy as is defined by NGSI, amongst others, with this CEF context broker. Now, how do we test and install stuff? We have started by determining a number of locations to conduct our first test. These were determined in consultation with the consortium, and we included different location types, both surface and underground water. And we are using 2 sensor tubes each time, one with the new imec sensor and the other one with some reference sensors. And we applied the same general operational procedures on all sensors venues to set up, calibrate, measure, and clean the sensors. Communication and stakeholder management. Well, there the usual suspects for dissemination are used. Conferences, website, newsletter, Twitter, LinkedIn, and we have also a dedicated YouTube channel. Now, what use cases have you already worked on? Sensor locations are being defined in collaboration with the consortium, as said, but also with a broader group of stakeholders. We have held a few stakeholder events on the topics of salinization and discharge in surface water in order to understand the stakeholder needs and see if they have specific locations in mind. On the bottom, you see all the possible locations we could use. Now, based on these conversations and the input from the consortium, an approach has been defined to define a first list of location, which is based on two criteria, namely general technical criteria and also specific use case criteria. For the general technical criteria, we got input from the Internet of Water partners. Namely, there we primarily asked ourselves, where can a sensor best be placed? We made a relative ranking based on technical suitability and accessibility, and also the accessibility of the mobile network coverage for needed data transfer was very important in determining where to put the new sensor locations. Now, there's also use case specific criteria. Again, input from the Internet of Water partners and stakeholders was taken into account, and some relevant, meaningful areas of locations to measure what we want to know. Also, what do we want to measure for what reason? And again, we made a relative ranking here based on substantive suitability with a focus on the use case salinization and discharge in surface water. Here, you can see that we use machine learning techniques to move from point measurements to predictions of river water quality. This example illustrates how we can deal with data from Internet of Water, for example, to create a dynamic salinization map of the coastal region. The dynamic salinization map shows how salt water from the sea flows into and retreats the hinterland throughout the year. In the summer, the salinization problem, the intrusion into the interior, is greatest due to the drought, of course. The predictions here were trained on the basis of existing stakeholder measurements from the year 2019. Imagine what we can do if we can have hundreds of sensors in this region to supply us the data towards our developed digital twin for predictive simulations. You can find more and the latest info on the Internet of Water project on the aforementioned website. Now on to project number 2. The same city of Antwerp is vulnerable to flooding, as most of the ancient city lies below the harbor waterline and is only protected by quays and some storm surges. But every now and then there are exceptional big storms that bring extra high waters from the sea to the river Schelde, called storm tides, and flooding is very much possible then. Certainly if also heavy local rain adds to the problem. So the objectives for the different stakeholders are the following. For the fire department, we need fast and correct 3-hour estimates of the water level on street level. And for the sewer department, we need proactive monitoring of sewage data and, of course, corresponding pumps to stop working at the event of a calamity. Now, based on real water levels in river and sewer system, and on top of that, we also need real-time rainfall sensors. Our algorithms process these real-time fused sensor data streams together with historical data on calamity events and their corresponding sensor readings, of course. And of course, we also use the forecasted rainfall from the national weather radars. Now, to provide predictive flooding models and water levels in the street for the next 2 hours, these algorithms are needed. Thus, the needed disaster teams of both fire brigade and sewer management company can act in a timely manner if things happen. Now, all the info ended up in some visual dashboards where both weather forecast, flood prediction, and sensor monitoring are combined. This, for example, is the estimated amount of rainfall in centimeters to be expected in the next 3 hours, which in turn gives an input to the trained flooding models, which in turn predicts where problems might occur on street level during the next couple of hours. As you can see here, the more blue it is, the more chance it is flooding will be there in these streets. As you can see, in this street, 80 centimeters of water is expected 30 minutes from now, based on all the sensor readings and the data at hand. As an added feature, also the current status of all the sensors can be monitored as well with the same backend of our system. Here, the pressure sensor is currently doing all right, but history shows water levels were higher than normal the last couple of months in this particular measurement point. Phase 2, there we will model to predict proactively the impact of showers in the street over 3 hours over the complete operational zone of Antwerp. And this will include modeling with feedback, namely, what can we learn if we compare the data of the application with the data of the real historical interventions? Is it possible to not only predict the impact of water, but also the impact on the citizens? And are there more predictive correlations that arise? Furthermore, we will be able to fine-tune the thresholds for preventive alarming based on the impact on a certain area rather than the intensity of the showers themselves. Also, research on how the output of the model can be used to determine external communications around floods, because miscommunication can lead to distrust from the population, and this support needs to happen with very high reliability. Last but not least, we will also try to link it with other city services, emergency planning service of the city of Antwerp, urban planning services, or even we link it with real-time mobility services. And last but not least, there's the Smart Water Grid project. Availability of water is under stress due to climatic changes. As already said, see the prolonged drought in Belgium for the last few summers. As such, the scarce resource water must be handled as good as possible. You see the quote here. In Flanders, it is a bit better, but still awfully bad, as 20% of all our drinking water is lost due to underground pipe leakages. And this costs a lot. Not only that, it's not the water loss and the costs itself, but if unlucky, these leakages can lead to further damages in the infrastructure, as can be seen here. A rupture of a water pipe was the reason that a train tunnel was flooded for over a week in Brussels in 2017, causing all kinds of economical, ecological, and societal havoc at the time. Now, where are we today here in Flanders? We can detect leaks in this zone, but the alarm that goes off is for a really huge zone, 70 kilometers wide, which in worst case scenario, a lot of human effort is needed to detect and fix this leakage. It could take weeks or even months to really detect the faulty pipe. Now, if we could narrow that down to street level, which means less than 1 kilometer of piping that has to be researched, well, a lot of positive vibes could happen. The search time to find the leak is just a matter of hours now. There's less hinderage for the end consumer. There's a faster service. There will be increased quality, and there will be increased consumer confidence in the end as well. Now, the solution to come to such a fine cloud-based leakage detection system is twofold. We are building a digital twin of the real-world situation at hand, where the AI model is fed with real-time sensor data to see if it holds to the prospective theoretical hydraulical models. Now, these hydraulical models indicate how water flows, and their calibration is required, and it is only for one particular flow scenario. So this, to maintain these hydraulical models, this becomes very labor intensive for many scenarios. So this is where machine learning will speed this up, as it can calculate many scenarios easily in parallel. And it will make these hydraulic models also more accurate. On the other hand, with machine learning alone, without these hydraulical models, it would require too many sensors in the field. So the combination of the two, having a hybrid twin, is really ideal and will be the real value. On top of that, we also want feedback from the end customers that will be used as a virtual sensor to improve the hydraulical model as well. This kind of multi-dimensional hybrid twin has never been done before, so to optimize all 3 dimensions at the same time will be a challenge. As said, research dimension 1 is all about the just mentioned hybrid twin to detect and localize water leaks with better accuracy and with limited measurements needed. A second research dimension is about developing new wireless sensors to better fuel this hybrid twin with real-time data about conditions of the water pipes. Here we will investigate how wired water sensors can be adapted to communicate wirelessly using LP1 technology, including potential pre-processing in the edge and optimizing operating parameters for such sensor networks. There we will use Aloxys technology to build this LP1 water valve position indicator and estimate the flow rates in the water pipes. And third and final research dimension is providing feedback to the hybrid twin to further fine-tune the predictions, which in the end will lead to better connected field services and a better customer service. What do we mean with better connected field services? Well, there, smarter workforce planning based on severity of the leakage and quality issue can be taken into account, or predictive maintenance based on machine learning. Their economical loss of the leakage versus cost of finding the source of the leakage will be taken into account. And furthermore, we will develop a technology platform where smart meters as components in the smart grid are directly connected with this field service process. For better customer service, there, how to deduct the leakage and water quality data to individual impacted customer accounts and their smart meters, or we could also use or develop a business rule engine to proactively inform our customers in the real world together with these smart connected meters. So compared where we are today, we have 20% of water loss, costing society in Flanders roughly 60 million euros a year. Now, if we go to our solution, the smart grid solution, it will bring back this loss from 20% to 7.5%. Okay, it will still cost the whole solution 9 million a year, but we already gain plus minus 7 million euros a year if we can deploy this solution. Also, the spiral diagram shows a minimum of surface if we take our smart water grid solution compared to these 6 possible variables. 2 POCs are being delivered. The first POC will be on smart and fast leak detection on a 1 kilometer range. And the second POC will be on proactive customer alerting, given that, of course, POC 1 is successful on the sub-kilometer leak detection deployment. Now, as we have seen in all 3 projects, water is a scarce product that needs to be handled as good as possible. So it can make a difference in society on multiple sustainable development goals. Now for me and imec, I have hoped that I have shown you that IoT together with AI can also make the difference. The technological future concerning water is bright. You should indeed wear some shades. Here are all the channels where you can reach me if you should have extra questions on these projects or want to see if we can do projects together. Thanks for having me, and I'm looking forward to the discussions afterwards.